Okay, thank you. Thank you, Evan. Thank you all you guys for coming. So I'm the last one. I'm very hungry now. Hope I can survive. All right. So I'm a grower, right? So basically what we're doing, we're growing material. What kind of material we are growing now? Uh, we can grow all the family members of a transition method that took us. Okay, using CVD method. So because the time is limited, I don't show here. All the families. Okay, more than 40 members now. Not only for the binary, we can also grow the canary and also four components TMD materials now. And the size is larger than 10 microns to like a 1 millimeter size. And the growing time is pretty fast. And we can grow to like a 1 millimeter size and create a monolayer in 3 minutes. So pretty fast. Okay, in terms of the growing method, uh, the very beginning one method people using the mechanical exfoliation, so they can make a high quality sample, but the output is pretty low. So sometimes a few days you can get one tiny flake, and then the chemists guys they develop this kind of a liquid exfoliation. So of course they can produce like a milligram, grams, even tons of this 2D materials, but they are good for energy application. Sorry, catalysis, but uh, for other applications like devices, electronic devices are not that good. So that's why we're working on this deposition method. So specifically, chemical vapor deposition, uh, molecular beam epitaxy or MOCVD. Okay, the good thing for CVD method is we can produce large size. As I said, as large as wafer size, even to like tens of inches. And also the cost is low. It's not that expensive to buy a furnace, right? And the precursors are also very cheap. We don't have to maintain the very high vacuum, and also the quality is good enough. How good? So recently we can produce some 2D materials, and we have demonstrated they are superconductor. So two of them. One is niobium diselenide, another is the moly ditelluride. So monolayer and superconductor, so which means the quality has no problem. All right, so this is a very classic setup for the CVD method. Basically, what we have is we have okay feeder here. There's a big furnace. It's not shown here, and we have this cold tube, and in the cold tube we have the precursors, the chocolate precursors, sulfur, selenium, and tellurine, and we also have this precursor for metal. Okay, metal oxide, metal fluoride, different things. We just put them here. And at the center of this cold tube, where we put our substrate, all kinds of substrate, right? Silicon oxide, quartz, and whatever you can, which can resist high temperature. So for the precursor, so for the TVD, for TMD, most of them are solid, okay, a solid precursor. So because of the solid precursors, which means it's, it's a complicated process. All right. Is it a solid reaction or this solid or gas reaction? Okay, there's no good answer by far, but some people that are working on this. So what we believe this kind of gas or small particle and some nanoparticle, what will happen? I show you what will happen. Okay, in order to grow the TMDs, all right, the first step is nucleation. Okay, okay, nucleation. What do we need? We need a metal, right? We need the chocolate. Chocolate has no problem. Sulfur, selenium, tellurine. I think the melting temperature is pretty low, like below 600 degrees. But for the metal, this is a challenging. Of course, like moly oxide, it's okay. At the melting temperature for moly oxide, 600 degrees, pretty good. But for tungsten, okay, tungsten the melting temperature is pretty high, like 150, 1,500 degrees. And the niobium is pretty high. A lot of metals that are not good for precursors. So the metal precursor would be the key to grow TMDs. So how to control it, how to find the best one with the nice melting temperature. This is the key. Alright, so this is melting, this is nucleation. Once we have a good metal precursor and chocogen precursor, okay, we find a good temperature window, like 600, 700 degrees, they meet together at the substrate, okay, we have a lot of nucleation, what will happen? Okay, they will react, right? And they grow, slowly grow or fast grow? If they grow slowly, what will happen is you will have like a flame, and the green side will be very small. But if they can grow fast, what will happen is you will have a big single crystal. All right. So the second key is we have to make sure the growing rate is as fast as possible. In that case, we can grow large grain size monoline materials. So enough nucleation and fast growing rate. So these are two keys. All right. For the sulfide, I don't waste of time showing how good it is. So at the very beginning, what we're doing is we deposit a quite thin layer of moly. Moly, this is a moly metal, and I think this 1 to 5 nanometers. And then we just use sulfur to sulfurize it. All right. So by this way, we can grow this large size monosulfide, like 1 centimeter size. But the quality is not that good. Why is this? Look, the result of small flakes, right? This one small flake means this one grain, and the grain size is a few nanometers, and also the thickness is not uniform. I think from 1 to 5 layers. This not good enough. So what we did is we replaced this moly metal with moly oxide. It turns out moly oxide is pretty good precursor for producing the moly sulfide. So this is why people now using the moly oxide. Okay, so often. Okay, by this method, we can produce a single crystal moly disulfide, shown here. And now, what we can do is we can produce like this triangle boundary, hexagons, stars, multiple layers, ribbons, and films. And the maximum size, okay, for the single crystal monolayer is 1 millimeter size. Okay, let's say something about these structures. For this triangle boundary, of course, there are only one group boundary here, right? I think really will be keen to this. And hexagons, hexagons, this is a single crystal. Okay, so stars, this is not a single crystal. There is a nucleation at the center. And we have 6 boundaries, okay, towards this point, this point, this point, this point, this point. So in PM, it's pretty beautiful. And the multiple layer molecular sulfide. This is another interesting story. Okay, so when we grow the TMDs, why most of the time we grow 1 layer, 2 layers? Can we grow 10 layers? Can we grow 20 layers? It's really right. It's really challenging. What's the reason? So we also think about this question. It's most likely between the competition of the aging growth and this interlayer growth. Okay, so they prefer to the detected growth at the edges, not the layer by layer growth. But they depend. How depends? Okay, for sulfide. Okay, for sulfide, it tends to few layers on one layer. For selenite, it is also you can easily to grow few layers, but for telluride, no. Telluride, most of the time you will get big sample, a few nanometers, 10 nanometers. So this is the nature of the different chocolate. All right, and also look at this shapes. Okay, sometimes we can get a triangle, sometimes we can get a hexagon star. Why this? Why this? I think a very important factor is the ratio of metal over chocolate. All right, if the ratio is very good, like 1 to 2, so most of the time we can get a perfect triangle and this perfect hexagon. What will happen if the ratio less than 2? We don't have enough sulfur. What will happen is, okay, look at this angle, look at this triangle. What will happen is, this side will bend inside like this. Okay, like this, and all the sides will be truncated like this or like this. Okay, so this is another interesting story. I don't waste time here. Let's go. And the telluride. Okay, telluride is more difficult than the moly the sulfide. So most of the time we need hydrogen to assist the synthesis. So this is a pretty big telluride one. Single crystal, 1.5 millimeters. So this is moly moly telluride. And okay, uh, so white telluride, okay. So people now can easily growing this sapphire and the selenite, but okay, both of them, they are semiconductor. They have quite similar properties, right? Telluride are completely different. Telluride is a metallic. Okay, telluride has different phase, one T phase, one T prime phase. And here I show you some key information for the telluride recently reported, like this non-saturating magnetic resistance. So this in WT2, and also the superconductivity, this in MOT2, and also the phase transition. I think both material have it, and of course the strong spin optic coupling. And I think this was very interesting. It's a wire metal. So telluride WT2 is a wire metal. So you can find the wire families in this material. I think more important, if we can produce monolayer WT2, that will be very promising candidate for spin Hall effect. So that's why people are working on the wire thin metal with the telluride. All right. So how to produce telluride? So tellurine, of course we have tellurine here, but tellurine is not friendly. It's not that active as sulfur and selenium. And so that we have to figure out some way, right? If we put like tungsten or tungsten oxide, molybdenum oxide, we cannot get it. We cannot get it because this oxide is not active enough. But how about we use chloride? Tungsten chloride. Tungsten chloride is very very active, but it's so active. So before the reaction, it's gone. Okay, the melting temperature is around 200, 300 degrees. So the strategy is mix them together. We mix this tungsten oxide, tungsten chloride together, and also we put some tellurine inside here in this boat. By this way, we can produce this tungsten telluride and moly telluride. Let's look at the geometry of this material. Okay, so this is side view of the atomic structure, and this is top view. So obviously, this is not 2H phase, right? This is 1T phase, and this is the WT2 monolayer because the 1T phase. So most of the time, it's growing like a ribbon. It's not like a hexagon, like a triangle ribbon. And this is also a lot area for the one monolayer WT2. And we can also see this boundary is not that clear, but we have sharp eyes. We can see it. Similarly, for the MOT2, it's also a ribbon, pretty long. I think it's more than 100 microns. It's low enough to see it. And we can see some 1 layer, 2 layer, 3 layer MOT2 here. And that's coloring. Okay, so this is a very typical image of MOT2 showing the crystallinity or the orientation of the crystallinity. It's not a perfect shape. It's like so many arms right outside. So that's determined by the nature of the atomic structure of these materials. But most of the areas, they're monolayer. But look at the inside, the center, this color, blue color, they are thicker. Okay, few layer or even a few nanometers. So I told you, telluride tend to be thicker than sulfide and selenite. All right, so of course we do the spectroscopy on this, the Raman mapping and the PL all showing this material is pretty good, homogeneously uniform monolayer. And now we look at this atomic structure of this material. So this is the WT2. So perfectly overlap with the schematic, the atomic image. And this 2H, the 2 layers, the 2H stacking, 2H prime stacking, and some group boundaries. We also see this. So actually, for this 1T phase WT2 MOT2, if you look at this this figure, you will see it's kind of quasi one-dimensional structure. Look, one-dimensional, right? This is one-dimensional. So I think one interesting topic is if we can isolate this one unit, what will happen for this one unit? What the properties of this single unit? Okay, single cell. This one, look, very narrow. I think it's only 1 or 2 nanometers. And if we go back to this, all right. Can you see it? There's some white lines. Why this? I tell you, it's because the white line is here. Okay, because it's not that strong, so it tends to break at this direction. So that's the reason got some white lines. Okay. Here is this STEM imaging of MOT2. Similarly, you will see some this quasi one-dimensional structures like this. Don't spend time with this. Okay. Now we make some devices, right? And then we find that for WT2, yes, we observe the magnetic resistance, and also for very thick one, we see the unsaturated one, but for the thin one, it becomes a kind of insulators. So we have seen this semi-metal to insulator transition in the WT2 if the thickness decreases. For MOT2, yes, we can see the superconducting behaviors. All right, for monolayer, even for monolayer MOT2, and the critical temperature I think is around 0.5 K. But for niobium diselenide, it's not showing here, right? That TC is much higher, 5 K. Niobium diselenide monolayers. All right. So in addition to this binary tellurides, we also produce the telluride. This is tellurine doped tungsten diselenide. It sounds complicated, but this is interesting. Why is it interesting? WSE2 is 2H. WT2 is 1T. If we mix them together, what will happen? So look at this circle. If the concentration of the tellurine is below 50%, so all the single crystal, they're hexagon, okay, hexagon shape. But if it's above 50%, it becomes something like a road, because below 50%, they're all 2H phase, and above 50%, there'll be 1T phase. This is the reason why it got different shapes. And also, below 50%, we can see there's a PL peak, but above 50%, there's no PL peak, meaning this is a metallic. There's no semiconductor. So it's another interesting question. How it happen? How it can translate from a 2H phase to a 1T phase? What will happen exactly? Okay, and the second telluride is this one. It's how to say? It's moly-doped tungsten telluride. Okay, now we put the two ions here, tungsten and moly, and this material turns out this is wire semi-metal. So this work we are collaborating with Hassan from Princeton University. They just do the opposite. Okay, so they can identify is it a wire semi-metal or not by looking at how many nodes here it is. For this example, we have 1, 2, 3, 4, 4 nodes here. So this is the very good evidence. I'm not physicist, so I won't spend a long time on this. But what I can share with you is if we tune the concentration here from 0 to 100%, we will see this material from kind of a topological insulator to wire semi-metal at some certain concentration. All right, I think pretty much. Thank you very much.